Hi everyone, I'm Anna and this is my Lab 3 video report for Physics 2 on DC and RC circuits. So in this lab, I use the PHYS circuit construction kit to look at how current and voltage behave in DC circuits and how capacitors change the behavior of a circuit over time. So the main goal of this lab was to apply charge conservation and energy conservation using Kirchhoff's node rule and loop rule to both predict and measure current and voltage in the circuits. And then we also focused on understanding how resistors and capacitors behave, especially how current and voltage change over time in RC circuits instead of instantly like in ideal DC circuits. So for the DC portion, I started with a simple series circuit using two 1.5 volt batteries, a 47 ohm resistor, and a 100 ohm resistor. And since the total voltage is 3 volts and the total resistance is 147 ohms, the predicted current comes out to be about 0.02 amps. And because this is a single loop circuit in steady state, I expect the current to be the same everywhere within the circuit. So when I measured the current, both ammeters read 0.02 amps, which matched the prediction exactly. This makes sense because if the current were different at different points, the charge would have to pile up somewhere, which would violate charge conservation. And then when an ammeter is flipped around, the current reading becomes negative, not because the current changes direction, but because it enters through the meter's negative terminal. I then measured potential differences across each element using a voltmeter. The batteries produced a 3 volt increase, while the 47 ohm resistor dropped 0.96 volts, and the 100 ohm resistor dropped 2.04 volts. When I add all of the potential changes around the loop, they sum to approximately 0, which confirms Kirchhoff's loop rule and conservation of energy. The reason the circuit isn't disturbed is because ammeters have very low resistance, while voltmeters have very high resistance. So the potential versus position graph helps visualize what's happening around the circuit. So the sharp jumps in the beginning correspond to the batteries adding energy, and then the sloped drops show energy being dissipated by the resistors, and then the flat sections just represent the wires. And since the electric field is related to the slope of the graph, the steeper slope across the smaller resistors indicate a stronger electric field there. And then once capacitors were added, the behavior of the circuit changed noticeably. So as a capacitor charges, the current decreases and the light bulb gradually dims instead of staying constant. Once the capacitor is fully charged, the current approaches 0. So with the 10 ohm bulb, the capacitor charged in 5.6 seconds and discharged in 6.7 seconds. With the 20 ohm bulb, charging and discharging took noticeably longer. This clearly shows that increasing resistance increases how long the capacitor takes to charge and discharge. So then to analyze this more carefully, I used a circuit with a 9 volt battery, a 200 millifarad capacitor, and a 30 ohm bulb. And then instead of just using the starting and ending values, I recorded the voltage at multiple time points from 0 to 24 seconds while the capacitor discharged. This helped reduce timing error and gives a more reliable result. So I recorded the capacitor voltage every 3 seconds, starting at 8.99 volts and ending at 0.12 volts after 24 seconds. And then when I plotted ln of V over V naught versus time, the data formed a straight line, which confirms that the voltage decreases exponentially as predicted by the RC model. So from the slope of the best fit line, I calculated the experimental RC value of 5.74 seconds. And then this is very close to the theoretical value of 6 seconds. And the small differences is expected due to timing uncertainty and difficulty measuring very low voltages near the end of the discharge. And then overall, the data shows a clear trend. Increasing resistance increases the RC time constant, which slows both charging and discharging. And then even though this experiment was done using a simulation, the theoretical model still assumes perfectly ideal components. In practice, small deviations arise from how voltage and time are measured in the simulation, particularly due to timing uncertainty and limited voltage resolution at very low voltages, which explains why the experimental RC value is close to but not exactly equal to the theoretical value. And then if this experiment were done with real components instead of a simulation, the results would be slightly different. A real ammeter has internal resistance, so placing it in the circuit would slightly reduce the current and change the voltage drops compared to what we see with an ideal meter. Similarly, if a battery were connected directly to a capacitor with no resistor, the ideal model would predict that the capacitor charges instantly. In reality, internal resistance in the battery, wires, and the meter limits the current, so the capacitor actually charges over a measurable amount of time. And then overall, the results from this lab support charge conservation, energy conservation, and the exponential decay model for RC circuits. So the small differences between the experimental and theoretical values are expected and can't be explained by measurement limitations and non-ideal behavior, even in a simulated experiment. Thank you so much. Bye.